All right, here we go, 7.2. Um, Before this section, up through 7.1, we have been studying polynomials of various degrees. It started way back in Algebra 1 when you were studying linear polynomials, x to the first, of the form mx plus b. That was a type of polynomial called linear. And then we went to x squared, and we've been studying those a lot this year. Anything that's x squared that we studied so far has been a quadratic polynomial. And then the previous section was x cubed. We call those cubics. That was a cubic polynomial. Well, in this section, we're going to kind of just study polynomials that have degrees larger than 3. And we're going to be looking at not so much the technicalities of how to work with them like we did vertex form or transformations, but we're just going to be looking at describing the behaviors of the graph. So first of all, what is a polynomial? A polynomial is made up of two words, polynomial. Poly meaning many, nomial meaning terms. So a polynomial can have many, many terms. Here's what a polynomial generally looks like. P of x equals. Don't get bogged down in all that. Just realize that you have powers of x in multiple terms, and this is in standard form. This is in decreasing order of degree. So x to the n would be your largest exponent, n would be your largest number, and then the a's that are in front of there, those are just called your coefficients, right? The coefficients have always been and still are the numbers in front of the x. The degree of your polynomial is the largest exponent. Got it? And when we write them in descending order of degree, we call that standard form. So we can classify polynomials by two different ways. We can classify them by their degree. Mx plus b, when it's x to the first, that's linear. X squared, that's quadratic. X cubed, that's cubic. There are two more that you have to memorize now. If it's x to the fourth, we call that quartic. And if it's x to the fifth, we call it quintic. If it's x to the sixth, we don't call it hextant or anything like that. We just say anything that's 6 or bigger, we call a 6th degree polynomial, a 7th degree polynomial, or a 100th degree polynomial, whatever the case may be. Okay. We can also classify them by terms. So you learned back in Algebra 1 when you had y equals x, that was a monomial because x is a single term. If you look at mx plus b, that's two terms, that's a binomial. When we were factoring by double bubbling earlier this year, we had our quadratic trinomials. There were three terms, and we had to do target product, target sum. So if it's three terms, it's a trinomial. After three terms, 4 and beyond, we just say it's a 4-term polynomial, it's a 5-term polynomial, so on and so forth. Okay? So you got two new terms to remember. By degree, quartic is degree 4, quintic is degree 5. And then you can start classifying by any combination. Like you can have a quintic binomial, you can have a quadratic monomial, you can have a cubic binomial, so on and so forth. You can combine the two. Now, I'm going to go through this vocabulary list right here. It's not going to be fun, but it's something that we need to go over before we get into example 1. You can come on in. Yeah, I'll fix the attendance at the end of class. All right, what we want to do is, whether we're staring at the equation or the graph, we want to be able to determine the degree of the polynomial. We also want to determine the leading coefficient. So what is the leading coefficient? Well, the leading term is the term that has the largest x in it, largest power of x. The leading coefficient then would be the number in front of the x in that term, okay? That's your leading coefficient. We want to also count the number of terms. That's going to be pretty easy. And then we're going to use it to name the polynomial based upon its degree and the number of terms. We're always going to want to identify the domain and range. Especially like what we did in the last homework where we restricted the domain, what happened to the range, we still might want to be able to do that. Here's an important one. We want to determine whether the degree is even or odd. That's going to affect the end behavior. I'm going to put a little star by this one. Determine whether the degree is even or odd. This just means, is the largest exponent, and they're always going to be positive integers, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They're never going to be like 1.5 or anything ugly like that. You're never going to see any square roots on x's. It's always x to a really nice positive integer power. If it's an odd number, if the largest exponent is an odd number, we say it's an odd degree polynomial. And just like x cubed and x to the first, they're going to have opposite end behaviors, right? Remember x to the first, it looked like this. It was straight. It came in the bottom, went out the top. X cubed, which is 3 and also an odd number, it looked like x to the first, but now it had a little bit of wiggle to it. But same end behavior. It came in the bottom and went out the top. If you look at your even degree polynomials, if the largest exponent is an even number like x squared, Don't ever forget x squared. That's your basis of comparison for so many things. 2 is an even number, right? So an x squared, 2 is an even number. It has the same end behavior. Top in, top out, or if it's negative x squared, bottom in, bottom out. So that's the first thing that you really want to understand. If it's an even degree, it has the same end behavior, and if it's an odd degree, if that number happens to be an odd number, it has opposite end behavior. All right. Now jump down to the very last check down here, because we reused the words even and odd, and it got confusing to some people in third period when they started working on their homework. If we talk about a function being even or a function being odd, and we don't mention the word degree, we don't say even degree or odd degree, we just say is it even or is it odd, that's talking about the symmetry of the graph. An even function has y-axis symmetry. That's your folding symmetry. Can you fold the graph on the y-axis and have it coincide with itself? You know what your most famous even function is? X squared. X squared is an even function, and it's an even degree function. It's even because it has y-axis symmetry. If you fold x squared on the y-axis, the graph lines up with itself, okay? That has y-axis symmetry, so it's an even function. An odd function is like x cubed. It has origin symmetry. And remember, origin symmetry is your 180-degree rotation. 180-degree rotation. So like our parent function x cubed, that was an origin symmetric function. If you spun it around 180 degrees, it looked exactly the same. It was the same graph, exactly the same graph. Okay? It is possible for a function to be an odd degree function, but yet not be an odd function. That is, it can have an odd degree for its exponent, but not have origin symmetry. Just like it's possible for a parabola that has an even degree of 2 not have y-axis symmetry. If we shift it left or right, it no longer has y-axis symmetry. So not every even degree function is an even function, and not every odd degree function is an odd function. Okay? If you don't say degree, we're talking about symmetry. All right, what else are we going to be interested in? We're going to be interested in finding the end behavior. That's always going to be as x goes to negative infinity and x goes to positive infinity. And I typically find them in that order. That's your left end behavior and right end behavior. We're going to be looking for intervals of increasing and decreasing. Where is the graph going uphill for what values of x? And where is the graph going downhill for what values of x? We'll be using interval notation, and we'll use parentheses only, which means we're going to be doing open intervals. Here's what's cool. We'll be determining the maximum number of possible turning points. What is a turning point? A turning point here is basically either a local max or a local min. These are like your vertices, okay? A local max basically is a hill, and a local min is a valley. These are your vertical about faces. Where does it go from increasing to decreasing or decreasing to increasing? It turns out that the maximum possible turning points, the max possible, is always equal to n minus 1, where n is the degree. So a cubic polynomial of degree 3 is going to have maximum 2 turning points. A quadratic of degree 2 is going to have maximum 1 turning point, and it does. It has exactly 1. A polynomial of degree 8 will have maximum how many turning points? 7. You got it? Now those are the possible turning points. It can have fewer than 7, but 7 is the maximum number of turning points. You're going to count the actual number of turning points just by looking at a graph, okay? Identify the extrema. This is going to be the local and the global. There's 2 types. The global means the highest or the lowest value on the entire graph. If it does exist, there can only be 1. You can't have 2 absolute maximum values. It's the king of the mountain or the king of the pit, okay? There's no 2 winners. Now, it doesn't have to have a max or a min. It could be that there's none. But then we're going to talk about local max or mins, and these are going to be hills or valleys, okay? These are the highest, lowest points in the areas around this. So let's just write this here. A local max is going to be a hill, and a local min is going to be a valley. These are your turning points, in other words. These are your turning points. We're also going to be interested in the zeros of the function. What's another name for the zeros? What else do we call them? They manifest on the graph as x-intercepts. Yeah. What's the other term that I use besides zeros? I use them actually more often than zeros. Rhymes with hoots, which starts with R. Roots. There you go. I'm pretty good at clues, aren't I? Yeah. Roots. Zeros are roots. Roots are zeros. They're also the x-intercepts. Just like before, we're going to be interested in those. And of course, I did say it up there, domain and range. Yeah. We're going to be interested in the domain and range, especially when the domain is restricted. Okay, let's jump into example 1. Let's see if we can figure this out. First of all, we look at the polynomial. The polynomial's name is p of x. How many terms does it have? 1, 2, 3, 4, 5. Terms are separated by plus signs or minus signs. So it has 5 terms. Everyone see all 5 terms? Are the terms written in descending order of degree? Yeah. Yes. What is the degree of the polynomial? That is the largest exponent. What's the largest exponent? 4. So we call that the degree. The degree of the polynomial is 4, and then it's written in descending order after that. 3, 2, 1, 0. So we call this what form when it's written in descending order? Standard form. Very good. This is standard form. It's written in standard form. The degree of the polynomial is 4. Let's go ahead and fill in something that's not here. Let's write this. What is the leading term to this polynomial? Well, that's the leading coefficient. Since you mentioned that, let's put that right there first. The leading coefficient is -1. What's the leading term? The entire thing, negative x to the 4th. Got it? The leading term is negative x to the 4th, and then the leading coefficient is the number in front of that x. Now, this is an important one. Let's put a couple asterisks by there because this is a teaching example. The leading coefficient, of course, is what type of number? -1 is what type of number? Positive or negative? Negative. Yeah, okay, good. Now, here's what's important. The right side of the graph, if the leading coefficient is negative, is going to go down to -infinity every single time. If your leading coefficient is negative, your right side of the graph, your right end behavior, is also going to be -infinity. Every single end behavior for every single polynomial in the whole wide world is one of two things. It's either positive infinity or negative infinity. It just so happens that if you know what the leading coefficient sign is, you can figure out the right end behavior's sign as well. And you can see on the graph over here that clearly, as we go out to the right end behavior, this goes down to -infinity. All right? If the leading coefficient had been +1, then the leading coefficient is a positive number, and the right end behavior is positive infinity. Got it? Okay? So if we'll just say this, if a sub n is negative, the right end behavior is -infinity. What is a sub n? First of all, I better say a sub n, that's your leading coefficient. If your leading coefficient is negative, the right end behavior is -infinity. If a sub n, the leading coefficient, is positive, then the right end behavior is positive infinity. The sign of the leading coefficient gives you the right end behavior. Now, look how we can use that in conjunction with the degree. The degree is what, did we say? 4. What type of number is 4, even or odd? It's an even number. So let's temporarily jump from there down to here. If the degree is an even number, that is, it's an even degree polynomial, then the graph is going to end up going in the, guess what? Do you think it's going to be the same or the opposite direction? Circle one. Well, let's look over here on this graph. What is the left-hand behavior? It's also negative infinity, right? Which means it's the same. So if it's an even degree polynomial, your end behaviors are going to be the same. Let's go ahead and write that right here. If even degree, you're going to have the same end behavior on both sides. Positive infinity on both sides or negative infinity on both sides. If it's an odd degree, if your largest exponent happens to be an odd number, then you're going to have opposite end behavior. Now that one's a little easier to remember because the word odd and the word opposite both start with what sound? Odd, opposite. Easy to remember. Odd, opposite, opposite direction. So if you want to know the end behavior, let's jump down to the end behavior now. It makes sense to answer the end behavior question next. As x goes to negative infinity and as x goes to positive infinity, you can always fill those in first. As x goes to negative infinity and x goes to positive infinity. Of course, this is your left end behavior. This is your right end behavior. If you have the graph, these questions are boring, aren't they? If you have the graph, these are boring questions. What's your left end behavior? Hop on the graph, head out to the left. We're going down, 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 down to negative infinity. What's the right end behavior? Hop on the graph, go out to the right. Where are we going? We're going down, 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 down to negative infinity. It's boring. What if we don't have the graph? Can we still answer those questions? The answer is yes. The leading term by itself will give us the answers to both of those if we know what to look for. Let me talk you through how that works again. We'll combine the two things that we just talked about. Because, in this case, because the leading term is negative, I know the right end behavior is negative infinity, right? Now, because it's an even degree polynomial, I know even degree polynomials always have the same end behavior. So if it's negative infinity on the right-hand side, guess what it now has to be on the left-hand side? Also negative infinity. So this one is negative infinity on both sides. There you go. It's that easy. If your degree had been 5, let's say, instead of 4, the right end behavior is still negative infinity, but now because it's an odd exponent, guess what the left end behavior would be? Positive infinity. It would be the opposite. So on and so forth. Okay? So that leading term, if you know what to look for, look at the sign of the leading coefficient, and based upon the degree, you should be able to determine both end behaviors. But if you have the graph, just look at the graph and take all the fun out of it, for Pete's sake, right? Okay. Let's retreat back up here. How many terms did we say it had? 5 terms. So if we were to name this by the degree, we would say that this is a quartic, comma, 5-term polynomial. Or you could flip it around. You could say it's a 5-term quartic. Quartic 5-term or 5-term quartic. It doesn't matter. Either one. Yes?
Oh, wait, never mind.
Okay.
Yeah.
You got it? All right. Now for the domain of the polynomial function. Guess what the domain of this polynomial function is? All real numbers, okay? In interval notation, we write that as x epsilon, negative infinity to infinity. This is going to be the same for all polynomials. Just a little FYI. Every single polynomial has a domain of all real numbers. That's one of the nice features about polynomials. They have a domain of all real numbers. Now, the range is not always going to be all real numbers. We saw this with x cubed, that the range was all real numbers. Just like the range for x to the first was all real numbers, we know this. If the degree is odd, then the range is going to be all real numbers. Just like x cubed, just like x. Anytime you have an odd degree polynomial, the range is going to be all real numbers. Is this an odd degree polynomial that we're dealing with here? No, it's an even degree polynomial. Now, because even degree polynomials have the same end behavior, they come in and go out the same side, there is going to be some absolute maximum or absolute minimum where it's bounded. This one opens down, so there's an absolute maximum. That's right up here. What is that maximum value? It's 7, right? So this graph covers 7 and everything below 7, but nothing above 7, okay? So we'll say this. If the degree is even, it's going to be bounded. We'll just say it's going to be bounded. So for us, the interval notation for the range is going to be y epsilon. It'll be least to greatest, remember. We don't say 7 to negative infinity. We say negative infinity up to and including 7 with a beefy bracket. Least to greatest. And you get the range, by the way, from the graph. There's no way for y'all to get the range from the equation. So if I'm asking you for the range, you're going to be given the graph. So that should be a pretty easy question. If I don't give you the graph and I ask you for the range, it's probably because it's going to be an odd degree function. Keep that in mind. Solve what algebraically? Yes, actually there is. In fact, so far we can get the information just from the leading coefficient, believe it or not. Now the range, there's no way to get the range unless we have the graph. And we need the calculator for the graph, or to answer the rest of this, like turning points and stuff, we need calculus for that. So there is a way to do this part down here that we haven't gotten to yet without algebraically, as you call it, but it involves calculus. So we're not going to use calculus, we're going to use the graph, okay? But that's a good question. Now, the number of zeros, what's the number of real zeros? How many real zeros do you see here? I see 1, 2, 3, 4. So it turns out that this is the maximum number of zeros a fourth degree polynomial can have. It can have up to 4 zeros. And I actually see the 4 zeros. What are the real zeros? Let's list them. It's x equals. It looks like it's pretty convenient. Negative 1, 1, 2, and 3. Pretty easy to list them. Negative 1, 1, 2, and 3. So while a polynomial of degree n can have maximum n zeros, a polynomial of degree n can have maximum n minus 1 turning points. So what's the maximum possible turning points this graph can have if it's degree 4? 3. Good. A polynomial of degree 99 can have how many turning points maximum? 98. Good. Now, it doesn't mean it has to have 98. It can have up to 98, but that's the maximum number. For x-intercepts, it can have the actual number of the degree, but for turning points, it's always one less. How many turning points does this one actually have? 3, right? We have a local, we call this a local maximum up here, a local maximum. Then we have a local minimum down here, and then we have another local maximum right here. So those are all, there's 3 turning points, which is the maximum number this function can have, right? Now think about it. What are the turning points? Estimate from the graph. This is where it gets not fun for me because we have to estimate these. Let's go ahead and see if we can estimate some ordered pairs for this. This ordered pair up here has a y value of 7. I know that for a fact. But what's the approximate x value? Not 0.5, but it's to the left, so negative 0.5. Yeah, I'll go with that. It might be actually closer to negative 0.4 or negative 0.3, but who cares? We're going to call it negative 0.5 because it's easy to remember. What would be a possible coordinate for this local min? Well, it looks like the y value is negative 1. We don't have to approximate that. What would the x value be? 1.5? I'll go with that. 1.5. So 1.5 comma 1. And then this local max over here, this one we have to approximate both of them. Ooh, gross. What's the approximate x value? 2.6. I'm going to say 2.5. If you want to say 2.6, have at it. And then what's the approximate y value? 1.2, 1.3. I'm going to say 1.5. We'll just make it easy. Are you okay with that? All right. We'll just say they're all roughly in the middle. Good. Now, it's important to know those points. And to answer Bryson's question, we can actually get those values using calculus or a calculator. We're not using a calculator. We're just estimating. And of course, calculus is several years off from here. So we're not going to do that either. But there is a way to do that using calculus. What are the turning points? Estimate from the graph. Well, we just did that. Let's write them down here. -5 or -0.5, comma 7, 1.5, comma -1, and 2.5, comma 1.5. All right, now those x values, where those local max and mins occur, are very, very important because they define where the graph changes from increasing to decreasing and vice versa. So if we want to know where this graph is increasing, the intervals, we're going to start by saying x epsilon. That means that we're going to look at the x values from left to right. So if you look at this graph coming in from negative infinity, it's already increasing, isn't it? It's increasing from negative infinity, it looks like, up to -0.5, and then it's decreasing for a while, but then it's increasing again from 1.5 to 2.5. So let's go ahead and write those out. These are x values now. So from x equals negative infinity, comma, up to -0.5, and then we put the union symbol, remember? Union from 1.5, comma, to 2.5. Those are the intervals where it's increasing. That's where the graph's going uphill. The next one, where's the graph going downhill? Well, it looks like it's going downhill from x equals -0.5 to x equals 1.5, and then everywhere to the right of 2.5. So let's write that out. We'll have x epsilon again to show that these are x values, not ordered pairs x, y, but x values. So from -0.5 all the way to 1.5, union 2.5 all the way to infinity, decreasing. Well, that's if we're looking at the y values. The y values go down to infinity, but we're looking at the x values. For what values of x? Where is this graph going downhill? Everywhere to the right. Everywhere to the right of 2.5, which is from 2.5 to infinity. That's why we put x epsilon right there. See that? When I put x epsilon, that means that this is from x equals 2.5, from x equals 2.5 to x equals infinity. X epsilon means that they're both x values. And it's not an ordered pair x, y. I'm glad you asked that question because a lot of people think that. All right. Now, for the global and local extrema, let's just look at this real carefully here. The global extrema, this is going to be the absolute max or the absolute min. There can be only one or none. One or none of each. It's like having in Texas, the governor is the absolute maximum. There's only one person that governs the entire state as a whole, and that is the governor of Texas, right? Abbott. Then you've got all these local cities that have their own governor, if you will. We call it the mayor, right? The mayor is in each town, so there can be several local extrema. These are your hills and valleys, and you can have more than one. All right, so let's look at the absolute maximum first. What is the absolute biggest y value on this entire graph? 7. So 7, which we already said was the local max, is also the global max. There's no y value bigger than 7. So 7 is not only the governor of the state, he's the mayor of Austin as well, okay, because he's also a local max. So we'll go ahead and say that we have a maximum, and it's going to be of y equals 7 at x equals -0.5, and it's a global max. Now, see how it says to circle 1? I'm going to conveniently cross that out because 7 is not only a global max, it is also a local max. So it's actually both. So we can answer that one as a 2 for 1. Now, does this graph have a global or absolute minimum? No. You know how we know there's no global minimum? It's going down forever and ever and ever to negative infinity. There's no lowest value on the graph. So there is, if you want to write a note here, there's no global max. Or, sorry, no global min. There is a global max. So that just leaves us with the other two local extrema. We have a local min of -1. So we have a minimum that's local of y equals -1, and it occurs at 1.5, x equals 1.5. And then we have another local maximum of y equals 1.5 at x equals 2.5. So again, notice I'm writing the y equals in there, and the x equals is already written for us. We want to keep reminding ourselves that the maximum and minimum values themselves are the y values, and they occur at x values. Now, the last thing that I'm going to ask you here is this, okay? This is an even degree polynomial. Check. It is an even degree polynomial. Is it also an even function? Question mark. No. Does this graph have y-axis symmetry? No. You can't fold this graph on the y-axis and have the right side lay perfectly on top of the left side. It doesn't work that way. So even though it's an even degree polynomial, it's not an even function. So I'll put a check for even degree, but an X for being an even function. Is it an odd function? Does it have origin symmetry? If you put your finger at the origin and turn it upside down, is it the same graph? No way, because right now it looks kind of like a fancy M. If you turn it upside down, it looks like a fancy W. Are M's and W's the same? Nope. So there is no origin symmetry either. It's not an odd function. So there's no symmetry. So now you can hopefully keep those two straight. Even degree polynomial? It sure is. Is it an even polynomial? No. There's no y-axis symmetry. No y-axis symmetry. But even degree polynomial? Yes. N equals 4 is an even number. If you want to put explanations behind this. And for odd function, no origin symmetry. All right, so that answers some of the questions that third period had when they were doing their homework. Do y'all have any other questions about this? It's kind of a boring problem, right? We didn't really calculate anything. We just kind of looked at it and described some of the features. Yeah. We had to know some terms, and we had to put 2 and 2 together. We had to know about the leading term sign and the degree to determine the end behavior. But I think we can figure that out. Okay, let's look at example 2. Doing something slightly different here. Use the graph at the right now to write the polynomial function whose leading coefficient is either -3 or 3 in factored and standard form. All right, so it's telling us that we're going to walk away at the bottom here with an equation in factored form and in standard form, and the leading coefficient is one of those two numbers, either -3 or 3. Well, you know how we're going to tell which one it is? Let's look at the right-hand behavior. Come over here to the graph. What's the right-hand behavior? Where is it going? Down to negative infinity. Because it's going down to negative infinity, the leading coefficient should be what? Positive or negative? Negative. Those two will always match up. Negative leading coefficient, negative right-hand behavior. Positive leading coefficient, positive right-hand behavior. Now, because it has to be the negative number, what should the value of a sub n be? -3. Okay, so our leading coefficient is -3. Got it. All right, now let's look at the left-end behavior. The left-end behavior is positive infinity now, right? Which is the opposite. It's the opposite end behavior. It's going up to positive infinity. So because the end behavior is opposite, should the degree be even or odd?
Odd.
Opposite, odd, opposite, odd, odd, opposite, odd, opposite, odd. Ah, ah. You got it. It's an odd degree polynomial. How many zeros does it have? 1, 2, 3. If I told you that that's the maximum number of zeros that this polynomial will have, you can tell me then that it does have 3 zeros. What are they? It's x equals what? Let's see. -1, -2, -3. How convenient, right? -1, -2, -3. Guess what the degree is actually going to be? If it has 3 zeros, the degree is going to be 3. How many turning points does it have? Let's answer that question. How many turning points does it have? It has 2. Is that the maximum number that a third degree polynomial can have?
Yeah.
It sure is. Now, this is interesting to note. Our parent function, x cubed, had 0 turning points, right? But it still had the maximum possible of 2. But the x cubed parent function had 0 turning points. This is a transformation of the x cubed parent function, because it is degree 3, but it now has lots of wiggles to it. It has 2 turning points, whereas the parent function has 0. Interesting to note. All right, how are we going to write it in factored form? Well, to write it in factored form, we're going to need to know the following theorem, okay? This is called the factor theorem, and I'm surprised it's not printed out already for you on here. The factor theorem, we'll write it down. Yes, sure. The factor theorem says if x equals a is a root of a polynomial function f of x, then x minus that number, x minus a, is a factor of f of x. If you know a root, you know a factor. If 5 is a root, x minus 5 is a factor. If -3 is a root, x plus 3 is a factor. Okay? You already know this. It works the other way around. It's actually an if and only if statement. If x minus a is a factor, x equals a is a root. Here's an example that we've been already using. Let's say I have factored x plus 2, x minus 3, and it equals 0. I told you that you don't have to physically set each of them equal to 0 and solve. You could. You could just use the factor theorem and say, hey, if x plus 2 is the factor, what's the corresponding root? -2. And if x minus 3 is the factor, what's the corresponding root? +3. It works in reverse. If +3 is the root, x minus that number, x minus 3 is the factor. And if -2 is the root, x minus -2, which is x plus 2, is the factor. It works both ways. If you know a root, you know a factor. If you know a factor, you know a root. And if you know a root, you know a factor. And if you know a factor, you know a root. So let's go ahead and see if we can write the 3 different factors that come from these 3 roots. If -1 is the root, what's the corresponding factor? X minus -1, which becomes x plus 1. Yes, yes. If -2 is the root, what's the corresponding factor? X minus -2, which becomes x plus 2. And if -3 is a root, what's the corresponding factor? X plus 3. Now, just for kicks and giggles and extra practice, let's say the function came over here and it passed through the point 5. If 5 is a root, what would be the corresponding factor? Not -5, but x minus 5. Yeah. Okay? Now, I'm going to cross that out because it's not part of the graph, but it gives you something to compare it by because all of these were negative. There's one where it's positive. Okay, so I can come over here now, and in factored form, I can write my equation. F of x, we give it a name. The leading coefficient we said was -3, so we'll put that in front. And then we just write the 3 factors, x plus 1, x plus 2, x plus 3. That's the answer in factored form. Your leading coefficient times your 3 factors from the 3 roots that we got. Now, here's where we're going to make up for not really doing much math today. We've just been kind of identifying features. We get to actually do some computation now because it wants us to write it in standard form. For a cubic, that's going to look like this. Ax cubed plus bx squared plus cx plus d. In other words, I need to expand out my factored form. How do I expand out my factored form? Multiply it out. Yeah, FOIL. Now there's all kinds of ways you can go about foiling it. There's four factors that I need to expand them all out together. Here's what I would tell you to do. Do the two factors first that have the largest numbers in them. So down here on your workbench, we'll call this our mathematical workbench. All right, x plus 2 times x plus 3. Those are the two factors that have the largest numbers in them. Let's FOIL that out. FOIL it out. You get x squared plus 3x plus 2x plus 6. You combine your like terms and you get x squared plus 5x plus 6. First, outer, inner, last. Now, that's just those two combined with each other. Now what I need to do is this. Now I need to take the next factor of x plus 1 and write it side by side with that new one that I just came up with. And I need to expand those out. Now, does FOIL work here? It's a 2 by 3. FOIL does not work. But you know what does work? The distributive property. Let me show you how to do this. You just start with the first one and the first one. Start with the first term and the first factor. And you distribute it to all three of those in the second factor. Okay, so we multiply. So we get x cubed plus 5x squared plus 6x. And if there were more than three terms in the second factor, we would just keep going. Blah, 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 blah. Once we're done with that, now we switch to the second term in the first factor, and we do the same thing. We distribute it to all three of those. That gives us plus x squared plus 5x plus 6. And if we had another term in the first factor, we would then distribute it to all three, so on and so forth. This gives you an algorithm that you can now use to expand any size polynomial times any size polynomial. It works better than FOIL. Okay. Now let's just combine like terms. I'll start with my x cubed. There's only one term with x cubed, so I'll underline it. There's two terms that have x squared, so I'll double underline them. That gives me 6x squared. There are two terms that have x's in them, linear terms, so I'll triple underline them. That gives me 11x. And then the last term that's not got anything is my constant. It's plus 6. Now, that expands the variable parts. But there's still one last thing to distribute, isn't there? The -3, the constant. So let me go ahead and bring the -3 down and write the x cubed plus 6x squared plus 11x plus 6 down here next to it. And we save this for the very end because we want to keep our numbers small as we go. There you go. Now you take a picture. I was zoomed in too far. Yeah. Okay. Now I can distribute the -3 all the way through, and I get -3x cubed minus 18x squared minus 33x minus 18. And now all I got to do is bring that up to the top. So let's copy that with our little lasso so we don't have to rewrite it. And in standard form, I'll say f of x. Don't forget f of x equals. Don't forget that part. And then I'll just paste it down here, and boom, there it is. Now, quickly, the last thing I want to ask is this. Is this an odd degree polynomial? Is it an odd degree polynomial? Yes, because 3 is an odd number. Is it an odd function? Does it have origin symmetry? Look at the graph. Does the graph have origin symmetry? If you flip this across if you rotate it 180 degrees, does it look the same? No, the negative x-intercepts become positive x-intercepts. So it's not an odd function, nor is it an even function. It doesn't have y-axis symmetry either. So is it possible for an odd degree function to not be odd? Yes. Can an odd degree function be odd? Yes. You just have to look at it. Okay? Does it have origin symmetry? If yes, it's an odd function. Is the leading exponent, the largest exponent, an odd number? If so, yes, it's an odd degree. Now, I'll leave you with one joke that I might have told you before, but I just like it so much, I'll share it with you. I told my wife, I said, honey, your dress is too tight. And she looked at me and said, then wear your own clothes then. And I was like, okay, there you go. That's the joke. That's the joke I'll leave you with, right?
Mr. Crocker, we'll be able to work on this tomorrow, right?
You'll be able to work on this tomorrow in class. Yeah.